Welcome back to episode 6 of the Cyber Bike project. Yesterday we got some stuff done. Not much done, let's be honest. I just went crazy for the day because I tried to find something and couldn't find something, and then I found it and then I was just like, why? Today is going to be different. Today is going to be difficult because, well, difficult for me, easy for you. I suggest you go get something to drink, something to eat, relax, get comfortable. This is going to be a long episode. There's going to be a lot of information. It's going to be a little bit information overload. Just a little bit information overload. Like, if information overload was here, then today will be up here. Yeah. There's a lot to go over. Calipers, brake calipers. Oh my god, so much to learn. So much. But first, let's go over what I've done in the meantime, because I said I'd do some stuff off camera, and I have. I've got quite a lot done off camera. Ta-da! See, I got quite a bit done off camera. This is what we got done. Quite a bit, right? I think so too. So, what is this? Well, this is the rear swing arm. I've imported a set of shocks from a previous model that I've used. I will put the information and stuff in here and link in the description to the GrabCAD model if I can find it again. I don't think I can. I might. I'll try. We'll see. It'll be down there and the thing will be here, right there. So, what did I get done? Well, you saw in the last episode we got the sprocket done and we mocked up this part of the rear swing arm, and what I did off camera was scrap that completely. I kept the sprocket, but I made the entire swing arm using freeform geometry. It's tedious, it's fiddly, it's a lot of just sitting there for about half an hour moving just 3 or 4 vertices until it looks right. It's not fun to watch. It's really not fun to watch. So you can see here we got the mechanism to attach the shock. We've got all the spacing for the... Why are you turning sideways? That is bad. Don't turn sideways. Thank you. We got all the spacing for the chain, the bike chain, and I started working on how the calipers are going to interact with the brake disc and the swing arm. There's not much in the way of space to do stuff here, so I might be scrapping the idea of having 2 calipers and 2 discs on the rear wheel. This is not normal. It's not necessary at all. You do not need 2 brake discs on the rear wheel. The brake on the rear is rarely used on motorcycles unless you're racing or doing some really, emergency, oh shit, I'm about to die braking. You don't generally engage the rear brake. It's just not done unless you do for powerful motorcycles that you don't want to pop the wheel. You don't want to do wheelies, well, you just tap a bit of back brake when you're accelerating and it keeps the front wheel down. They do this in Superbike and MotoGP when they're racing. Keep the front wheel down when they're accelerating off the line. Same thing. So, I'm not happy with this hook thing at all. I may change it. I might get rid of one of the rotors on the back here and just have the one on the other side. But we'll see. We need to discuss something that's a little bit more important, because for the spacing of the rear swing arm, the clearance between the swing arm, the mudguard, the chain, the sprocket, rotor, tire, and the rim. There's a lot that I just listed there, and it all has to sit within a certain amount of space, and there's lots of fast moving parts, spinny bits, stationary bits, bits that are sliding against each other, bits that are engaging in each other, like the chain and sprocket. There's a lot going on in a rear swing arm and a rear assembly on a motorcycle, and it all has to work. Has to. If it doesn't, shit explodes. If you've never seen a chain come off a rear sprocket when a bike's moving, go look it up. It's insane. So, that's what we got done off camera. Quite happy with the amount of progress. A couple of things I still need to do, I need to research and learn how to do, is a travel multiplier assembly for the shock absorber. Normally in rear swing arms, there's a couple of other linkages and levers that are arranged and linked up in a certain way that when the swing arm moves a small amount, then it multiplies that travel through some linkages to the shock absorber, so that the shock absorber actually moves further than what the swing arm did and reduces the force applied to the shock absorber. So it's a travel multiplier but a force divider, and that's through some complicated linkages. Not really complicated, but I need to go learn how to do that so that I can do it, because at the moment this is not right. Having it directly applied like this, it won't work. There's going to be too much force and not enough travel distance allowed through the shock for this to work properly, so I have to go learn how to do that. But today's video is not about that. Today's video is about brake calipers. So, brake calipers. Oh boy, there is a lot going on with brake calipers. Brake calipers are a complicated subject. There is a lot going on in brake calipers. There's a lot of moving parts, there's a lot of engaging parts, there's a lot of stationary parts, there's a lot of non-stationary parts, that's moving parts, but not moving parts, like non-stationary meaning they move, but they're dynamic. They're non-stationary dynamic parts that change over time. For instance, the brake pads, as they wear, their thickness changes, which means your other moving parts like the cylinder head has to travel a different distance and be in a different position to what it is with a brand new brake pad. There's a lot of stuff going on. You have thermal engineering, ablative engineering, hydraulic engineering, mechanical engineering, of course. There's a lot of different things that are going on that have to be accounted for when designing and considering how brake calipers work. The other thing that needs to be considered is industry standard. Now, here's a topic we're going to have to come back to time and time again with this project, because with motorcycles, industry standard is, it's the industry standard. A lot of companies make parts, consumables like brake pads. There's a list, okay? There's a list of stuff, tires, all that stuff. They conform to industry standards. Things are same across the board, so you can go to a shop and you get a non-OEM part to replace the part on your vehicle at a lower cost or whatever. You just want something different. They all follow certain rules, and we're going to have to apply those rules through this project. And one of those places where this is really critical is brake calipers, because the brake pads aren't made by the OEMs. They aren't made by the motorcycle manufacturers. They are made by brake companies, and they have standard forms, shapes, and design. Yes, sometimes a big OEM manufacturer will come along and say, okay, we need a caliper that looks like this because it has to fit on our new bike, and they make a new pad and that works for it. We're going to have to do something similar. We're going to have to go, right, what kind of brake pad are we using? What kind of caliper are we using? And then I'm going to have to get my hands on it to get the dimensions and stuff, or if I can find the dimensions of that pad and its operating standards online, then I will do that, which is probably what I will do. Google is your friend. You need to use Google more often. So let's talk about what kinds of brake calipers there are and what are their differences, what are their pros, and what are their cons. In the majority, there are three main kinds of calipers, and there are two families of brake caliper. You have your single cylinder and your dual cylinder. Now, this is not counted by the number of cylinders that are on one side of the rotor. This is counted by the number of cylinders you have on each side of the rotor. Some calipers have a cylinder on just the one side, and then there's a mechanism that equalizes the pressure on the two pads. One of the simplest versions of this kind of mechanism is the pivot caliper. This works through a simple process of you have a pivot point here and you have your single cylinder here. When the cylinder engages and changes the position of the pushes on this pad, the entire assembly shifts, and when it shifts, it then applies pressure equally on the other side. This means that your pads, as you can see here, have a trapezoid shape. Is it trapezoid? No. Scalene? I think it's scalene. No? There's a name for this. Anyways, they still try and wear evenly, but the point is that they start off uneven, and you only have this limited lifespan of pad at the bottom here, and you end up wasting this much pad at the end of the pad life, which isn't, you don't go all the way to the bottom. It's really unrecommended to go to the bottom of your pads. This is probably the most simplest design of single cylinder caliper, but I don't like it. There are other problems involved. If your alignment to the disc rotor, or the disc rotor has a warp in it, or a bend, or a damage, these things create violent vibrations in action and all sorts of other problems that I really don't want to deal with. So this one is a no-no. The next kind that we have is the floating caliper. It's the same principle. You have a single piston on the one side, and when this cylinder engages, then the entire assembly will float on, it's usually on a set of rails with rubber bushings, and the entire assembly will then move this way, which will engage the pad on the other side with an equal amount of force. These are very common, but as you can see, it requires a floating point, or there's a point of friction. They're actually very simple to manufacture. They're one of the most common brake calipers out there. You can see this is for a vehicle with a vehicle rotor. It's much thicker. They work very well. They're space efficient, so they don't take up as much space in a vehicle inside the wheel assembly, and that's why they're commonly used on cars and stuff. But the caliper with the most performance is the dual cylinder caliper. And the dual cylinder caliper is also probably the hardest to manufacture, because you have internal channels for the hydraulic brake fluid to travel through. All of these different calipers are generally all cast materials. Some of them are billet machined housings. Some dual cylinders are split. This is a good example of a split caliper. You have a machined, it starts off as a cast, but they do billet machine. It's either cast or billet machined caliper housings. You have two parts. They are secured using screws. One of these screws is a special kind of screw that has a through hole. It allows the hydraulic fluid from the one side to travel to the other side and equalize the pressure of hydraulic fluid against the two pistons. This is a 6-cylinder pad, but it is a dual cylinder caliper. These are very high performance, and this one in particular is the one that we're probably going to model after for our perimeter rotor. Thank you, Ivan, in the comments of the last video for suggesting it is called a perimeter disc. That does seem to find more results on Google when you use those terms. So this is the caliper that is used on the Buell motorcycle. Now, we're not going to go out and buy Buell motorcycle parts because I had a girlfriend with a Buell and the parts are expensive. They are very expensive, and we will more than likely only go with the pad itself. And we'll find dimensions for the pad and design the rest of our caliper around the pad. These are special in the way that the pad attachment points are on the inside of the radius. They're on the inside of the radius of the design, whereas normally the connections and the bolt-on point are on the outside of the radius because the rotor is on the inside. This is what we're going to go with, but the number of types and designs are so many and so various. This is a single cylinder floating design. This is similar to what's on my dirt bike. So you've got a single cylinder, it's one-sided, and it is also on a floating rail. You have your attachment mount here, which attaches to the axle and the front forks. And then on the top of this, you have your floating carriage where the caliper itself, which is a single piece, floats using these pins, and it slides and we're in position to equalize the force on the pads. We have other things that we can consider later on, which are things like the master cylinder itself, which is the hand trigger thing on the handlebars. That uses a system that allows for compression, force release, return of hydraulic fluids. This is a simplified cutaway of how that works. This is a external radius caliper design. This is a Brembo brakes design for motorcycles. This is one of the more difficult ones. I believe this is a single piece unit. So when this is cast, there is a negative. The negative of the fluid channels and the cylinders is a sand casting that gets placed inside the die cast. That when they cast it, they then cool it down and then they can flush out that negative with water and whatever. I don't know how they do it, but I don't know how they do it specifically, but I understand the concept of using negatives inside of molds to create cavities. And yeah, so that is the quick and dirty of brake calipers. It's not the most interesting thing in the world, and if you're like me, it is pretty freaking interesting because there's so much to get into. The other thing that we're going to get into in this video just a little bit is O-rings, rubber. We have to talk about rubber. Before I get into that, I just have to do a shout out to John Kraus on Twitter. This shot of the Falcon 9 launch just yesterday. Oh my god, wow. My new desktop. Go check him out on Twitter. John Kraus Photos. He took a couple of really freaking awesome shots of the Falcon 9 launch through the sunrise. I'm not sure. I live in a different time zone. But yeah, shout out to him. That's a really cool shot. But let's talk about O-rings. So, when you need to learn how to do something, Google is your friend. I love Google. Google taught me so much. When you design things like calipers, there are seals. Seals that stop your hydraulic brake fluid from blowing out all over the road, all over your bike, all over you, all over your passengers, all over the pedestrians on the sidewalk, and the old lady walking her dog. You need to know about O-rings. I needed to know about O-rings for a different project when I did my own product design for a vaping product. I needed to learn how to use O-rings for a particular part of the design, and I had to learn how O-rings work in a mechanical sense. So, simple questions like O-ring compression, because they squeeze, will get you Google results like this. Selecting the correct O-ring seal squeeze ratio, the Parker's, or O-ring design. There, you just go through until you find stuff that gives you information about O-rings. I've selected these couple of websites. Parker's, they have, now I mentioned which video, it was a video, I mentioned that if you don't know how to do something, and if you can't find it within the first half an hour of Google searches, then you will have learned how to do that thing. But if you do find it, you will quite often find things like handbooks, or clicking on links like this, O-ring ebook. The e-handbook will give you all sorts of information about O-ring basics, types of seals, O-ring elastomers, This tells you about the different materials that O-rings are made from and what kind of material you want in your particular use case. Is there heat involved? What kind of pressures are involved? Is your O-ring a rotationally confined O-ring, which means you have an O-ring in a part that only turns, or do you have a sliding confinement where you have a piston and you have something that has to slide against an inside wall or an outside wall? So you, like I was saying, you have your static O-ring seals, failure modes. All of these different types of information are here on the internet. They are available because engineers and designers of stuff don't know everything. By definition, we cannot know everything. There's everything online, and we have to go do stuff like this. We have to go find stuff and learn how to use that stuff to achieve the results that we want. This is one of the big misconceptions about engineers that people have. Engineering isn't about going to a university and getting a degree. Engineering is about understanding the principles of how things work and being able to learn how to find that information out to do it yourself. That is engineering. It's got nothing to do with going and getting a degree. It's all about understanding the principles of stuff and how to work stuff out for yourself. And that's my opinion on it, the subject, and I'm sticking to it. And proper engineers, I'm sure, will agree with me, because way back in the day, before you had to go to university to get an engineering degree, we had engineers. They used to run trains. They were apprenticeships. People were taught how to do things from a senior or a mentor, or they just learned how to do it themselves. At some point, somebody had to figure something out in the first place, and nobody taught them how to do anything. They had to learn how to do it themselves. And that's what I feel engineering is about, being able to learn how to do something for yourself. So, yes, there's a lot to go over with the O-rings. We're going to need to use O-rings, and we're going to have to go over how O-rings operate and how they compress, because selecting the right diameter of O-ring cross-section for the type of groove, so that depending on how much it needs to compress with the other surfaces, will give you a certain amount of surface area compression seal ratio. It's important for the hydraulic pressure that is going to be behind the ring, how much compression seal that we need, the surface area, all that sort of stuff. You don't have to get into the weeds of the math on how to work it out, because quite often you will find tables like this, or in the case of this, there is more than likely a calculator tool. See, O-ring calculator with complete design analysis. There's going to be tools like this available online that will work the stuff out for you. You just have to put in your requirements and your parameters, and it will spit out what you need. You don't have to know how to do everything to be an engineer. You just need to know how to find what you're looking for. And that's the key thing about this YouTube channel, is me going to be explaining, or me showing you how to do these complicated things without being a super genius, because I'm not a super genius. I just do crazy shit. So yeah, I think we'll wrap this episode up here. We've gone over a lot of information. Off camera, I'm going to start modeling up the parts for the calipers and all that, and decide whether we're going to stick with single or dual rotor on the back. I'm probably going to just ditch one of the rotors and go with a single rotor on the back. So next episode, calipers will be done. I'll go over the parts in the calipers, how you work out tolerances and how everything fits together, how you model the O-rings in their functional state, because how you design an O-ring in its function, like in a dynamic system, is different to what it looks like when it comes out of the packet. You want it to have that squished profile to show how it's going to fit inside of the housing, so that you get the correct seating for your parts at the end when you manufacture them. Lots of information overload today. I hope you're all still there and your brains haven't exploded. Yeah, like, subscribe, check me out on Twitter, and I'll see you guys next time.